Okay, so welcome back to the continuation of pulmonary physiology. We left off on the last online lecture talking about partial pressures and what those are and how those are important. So now we're going to be talking about how we get oxygen from the ambient air into our tissues, right? So we need to go through all of those steps, and we're going to explain why and how this is done in just a second. So we know that the partial pressure of O2 in the ambient air is about 159 millimeters of mercury, right? So we need to get that oxygen from the ambient air into our alveoli within the lungs and then into our bloodstream. The partial pressure of the alveoli, represented as P capital A O2, is about 102 millimeters of mercury. Okay, this gives us about a 60 millimeters of mercury gradient to get air from the ambient air into the alveoli. So that gives us a nice 60 millimeters of mercury gradient to get from the air into our lungs, into our alveoli. The PaO2 is 102 because it is decreased due to the moisture being added to the air from the water vapor pressure, which is actually 47 millimeters of mercury. Now, the blood in the pulmonary capillaries has pretty much been stripped of most of its O2, giving us a P small v O2 of about 40 millimeters of mercury, right? That makes sense because this is the blood that's coming back to the lungs from the body to get oxygenated again, to go to the heart to be pumped back out, right? So the mixed venous blood, so venous blood meaning on the venous side of circulation, we're going to have a less amount of oxygen, right? Because we drop some oxygen off at the tissue levels. So that means we're going to have the venous side of circulation should have less oxygen compared to the arterial side. Right, so the blood in the pulmonary capillaries, which has been stripped of most of its oxygen, gives us a PVO2 of about 40 millimeters of mercury. So that gives us about another 60 millimeters of mercury gradient to move oxygen from now our alveoli into the mixed venous blood, right? So we want to get that oxygen into the blood somehow. So we had now that oxygen was in the alveoli, which partial pressure was about 102. Now we need to get it into the mixed venous blood, which is about 40 millimeters of mercury. Again, that gives us another about 60 millimeters of mercury, nice wide gradient to move O2 from the alveoli of our lungs to the mixed venous blood. The exchange between the alveolar air and the mixed venous blood will result in the systemic arterial pressures, right? So now we're going to have systemic arterial pressures, and the partial pressure of the arterial blood is actually now 90 millimeters of mercury. Pa small o2 is now 90 millimeters of mercury. Okay, so we have oxygen, which is in the ambient air. We have taken it in, it has gone to our lungs and into our alveoli, so it gives us a nice gradient of 60 from the ambient air into our alveoli, and then again from the alveoli we need to get it into our bloodstream. So our mixed venous blood, which has been stripped of most of its O2, is down to about 40 millimeters of mercury. It exerts that amount of pressure. The combination of transferring oxygen from the alveoli to the mixed venous blood results in our arterial blood's partial pressure of oxygen, which is going to be 90 millimeters of mercury. Now remember, on this slide we're only talking about oxygen. We're not talking about any other nitrogen or carbon dioxide here. We're just talking about oxygen. So then now we have our arterial pressure, P small a O2 of 90 millimeters of mercury. Okay, so now we can just look at these two diagrams, and it's better to get a visual when you look at it. So we inhale, we take in some air, goes through our trachea, comes into our lungs, right? Goes through our bronchi tubes, our primary bronchus, all that other good stuff, goes into our branches, our secondary, tertiary bronchi, and so forth. And then we get to the small level here, right? So we're going to zoom in over here to this diagram, right? So we get all the way to the end. So this little spot over here, we have all of our alveoli at the end of all these terminal bronchioles, right? So we go over here and we zoom in. This is where gas exchange is going to occur. So we have our terminal bronchiole and then our respiratory bronchiole, which leads right into our alveolar sacs, which encompasses, and then we have our alveolar ducts, and then we have our individual alveoli. So we have these little balls right here. This is an alveolus, right? So then we see all of these capillaries are actually completely surrounding the alveoli. which is good, and it's good that they're surround them so closely because that enhances diffusible surface area, decreases diffusible surface distance, so this enhances exchange of nutrients such as oxygen and carbon dioxide. So we can see there, so to give you a visual, we have to, all this is governed by pressures, right? So the pressure in the ambient air, let's say, is out here, comes in is about 159, we come into the alveoli, which is here, which is where we want to get the oxygen to. This is about 102 millimeters of mercury, and then right over here, the mixed venous blood, which is coming back to the lungs, or which is coming back up through. We mix that with, from the alveoli, partial pressure, which is 102, to the mixed venous blood, which is about 40, gives us another 60 millimeters of mercury gradient, and then that results in our systemic arterial partial pressure of O2 now, which then is 90. And we need that to be high, which I'm going to explain next while we exercise. All right, so let's now talk about exercising and these partial pressures. So when we exercise, we become what's called hyperpnic, or something called hyperpnea occurs. This is, the definition of that just means your increased rate and depth of respiration. So we're increasing our ventilation. So hyperpnea, or if we become hyperpnic, it means we're increasing the rate and depth of respiration. And then when we exercise, of course, we increase our ventilation. The increase in ventilation will increase the alveolar partial pressure of oxygen, so P capital AO2, which is important in order to keep the arterial partial pressure high, so P small AO2. A high arterial blood partial pressure is necessary to facilitate exchange at the muscle tissue level. That makes sense, right? Because arteries are carrying blood to the muscle tissues. We need that partial pressure in the arterial blood to be fairly high because we want an efficient exchange at the muscular tissue level, right? So the wider the gradient, the easier of movement of oxygen or nutrients from one location to the other. So again, like I said from the beginning of class, everything is governed by our 3 gradients that we have. Everything in our body is pretty much governed by gradients. Okay, so the partial pressure of oxygen in the muscular tissues are lower than the PaO2 in order to facilitate exchange, right? So the partial pressure of oxygen in the muscle tissues does not have a specific value. Like I was saying, that the partial pressure of ambient air is about 160, 159, 160. Alveoli is about 100, and then the mixed venous blood is about 40, which give us our arterial pressures of about 90, right? The partial pressure of the muscle tissues varies depending on the metabolic activity at any one point in time. So the pressure, that partial pressure of oxygen within the muscle tissue itself is going to vary depending on metabolic activity. But that's why it's very important that we keep our P small AO2 high, because we want to facilitate exchange efficiently at the muscle tissue level, especially when exercising. Okay, so these partial pressure differences are critical with regards to exchanging oxygen from the ambient air all the way down to the muscle cell level. Okay, so we're going to continue talking about different pressures, but now we're going to be talking about pulmonary pressures and how this governs movement of fluid through our tubes or through our vessels. So pulmonary pressures are important with regards to movement of fluid through our vessels or our tubes. The pressure in the right atrium is about 3 millimeters of mercury, and the right ventricle is about 25 millimeters of mercury. The blood is pumped into the pulmonary arteries, where the average pressure is now about 15. The pulmonary capillaries is about 10.5 millimeters of mercury and 9 millimeters of mercury in the pulmonary veins. This then brings us to the left side of the heart, where the left atrium is now 8 millimeters of mercury, and then the blood is ejected systemically at 120 reference person millimeters of mercury. Now we're in the high pressure system. Remember, left side of the heart, high pressure system. The mean pressure in the systemic arteries is about 90 millimeters of mercury, and systemic capillaries is 20. The systemic veins exert about a pressure of about 10 millimeters of mercury, which then brings us back to the right side of the heart, where the right atrium again is 3 millimeters of mercury. These pressure gradients are crucial for us to have ability of blood flow through the tubes, right? The smaller the vessel is on the pulmonic side, the more smooth muscle you will find, and are innervated by sympathetic vasoconstrictor fibers, which gives us the ability to have some selective constriction as well. Okay, so we see here, if we were to start here, very low pressure, but we need it to be low pressure coming to the right side of the heart, right? Because look at the systemic veins coming back to the heart. It's only at 10 millimeters of mercury, so we need it less here in order to govern flow into the right side. Then we pump the blood out of the right side of the heart. This is going to our lungs and so forth, but again, this is very low, about 25, right? Which averages about 15, like we said, so 15 millimeters of mercury pressure. We're going to come into the pulmonary capillaries, which is about 10. See, we still have lower to higher to lower to lower, so we can govern movement through these tubes, right? So then we can go into 9, which is millimeters of mercury into our pulmonary veins, which then comes back to the left side of the heart. Now we just picked up a bunch of oxygen here. So we are back at the left side of the heart, and then now, boom, we're in a high pressure system and we pump out at 120. And then now in our systemic arteries, we have about an average of 90 millimeters of mercury, which then we come down into our arterioles and then our systemic capillaries, which is 20. And then when we give off exchange in the muscle tissue level, then we head over to the venous side of circulation, which then again, 20, we go down to 10. So this is what pretty much governs movement of fluid through the tubes, through pulmonary pressures. And again, we need those in order for us to have movement through our system and keep coming back to the heart and keeping ejected and everything flowing and so forth. Okay, so I'm going to start talking a little bit about what respiratory exchange ratio and what that means. So the respiratory exchange ratio, or RER, which is abbreviated to, is the amount of carbon dioxide produced relative to the amount of oxygen consumed. So it's represented, the equation is VCO2 over VO2. So again, that's the amount of carbon dioxide produced relative to the amount of oxygen one is consuming. Okay. What does this represent? This represents the fuel that is being utilized. So substrate utilization is what it means. The ratio actually goes from 0.7 to 1.0. A ratio of 0.7, you are mainly using fats as a substrate. At a ratio of 0.85, you are using about an equal mix of carbs and fats. And then a ratio getting up towards 0.9 to 1 to 1.1 or so, you can get up to 1.1. You are mainly using just pure carbohydrates at that point. You are purely anaerobic at that point in time during the exercise. So our RER will increase as exercise intensity increases, right? So if we were to put someone on the treadmill and hook them up to our metabolic system, put the mask on, do all that good stuff, we will be measuring the amount of oxygen that is being consumed as well as the amount of carbon dioxide is being produced. And one of the calculations that the system does is it shows us a line of RER. So it does that calculation for us where it's VCO2 over VO2. And we can take a look in the lab that where someone's at 0.7, it means they're if they're walking or jogging, they're mainly burning fats at that point in time. As exercise intensity increases, they are mainly going to be relying on their carbohydrate system. And that's something you can see in lab, which hopefully you will be able to see at some point in time, right? So our RER increases as exercise intensity increases. This gives us an indication of what the athlete is utilizing mainly for a substrate at that time. A trained individual will be able to be a better fat burner, so can keep their RER lower for a longer period of time, right? Remember I said a few lectures ago we talked about chronic aerobic training. People can become better fat burners, which then spares glycogen. So sparing glycogen meaning, which is what you want, because then at the end of the exercise, you're going to use that glycogen for that last kick. Right, so as the RER approaches about 1.0 to 1.1, we know that the exercise task will soon be coming to an end. Again, why is that? Is because how long can we work non-oxidatively? Only about 90 seconds to 2 minutes, right? If you recall back in bioenergetics.
So RER increases with exercise intensity, just as lactate levels do, and we're going to get into that in the next video as well. We're going to finish talking up about carbon dioxide pressure gradients, and a couple things about the ventilatory threshold and whatnot. And so we'll head into our last lecture now.